Uh, we plan to discuss the choice of refrigerants, also called as selection of refrigerants in the HVAC and refrigeration systems. We have already defined refrigerants as an important working fluid used in both the refrigeration systems as well as air conditioning system, and it performs a key role in cooling the space by extracting the heat from the space to be cooled in the evaporator of the refrigeration system. So the choice of refrigerant, which refrigerant to choose, is not random. It is a multi-parameter engineering decision, and we need to consider the thermodynamic properties, the physical properties, the chemical properties, as well as the environmental properties while we select the refrigerants. Not only that, we need to be aware of the compatibility issues, especially whether the refrigerant will work with certain materials or not, how it will affect the lubricants which are used in the refrigeration system, as well as we need to be aware of the regulatory aspects of the refrigerants, especially in the context of ozone depletion and global warming. When we talk about the thermodynamic properties, what we mean is basically the properties like boiling point, the performance of the refrigerant in terms of system efficiency, that is, coefficient of performance, and the effect of the refrigerant on the compressor life. All this is going to matter. Important property, and I would say the most important property, thermodynamic property, in the selection of refrigerants is what is known as the normal boiling point. By the term normal, what we understand is the boiling point at atmospheric pressure. So the key requirement is that the boiling point should be lower than the required evaporator temperature. Means, for example, if I want to achieve domestic refrigeration, wherein I need to maintain the temperature, system temperature at below 0 degree centigrade, then the refrigerant should boil at a lower temperature than the evaporator temperature. So, for example, R134A, which boils at minus 26 degrees centigrade, would be then suitable for domestic refrigeration. Similarly, if you take another application like an application of achieving minus 80 degrees centigrade in the ultra low temperature cascade system, there the choice of the refrigerant cannot be R134A because we need to have the boiling point lower than the required evaporator temperature. So for that, ethane, which is R170, becomes the obvious choice for the refrigeration system. The key consideration is why the boiling point has to be lower than the required evaporator temperature is we basically want to have a positive pressure in the evaporator. If the boiling point is not lower, normal boiling point is not lower, then we need to operate that system under vacuum. And operating the refrigeration system under vacuum is a costly affair because maintaining vacuum in the evaporator would be a challenging aspect. So, along with the fact that normal boiling point is an important parameter in making sure that the required low temperatures are met, it also ensures that the evaporator is always operating under positive pressures. So, the key property is that the normal boiling point should be much lower than the required evaporator temperature so that the evaporator pressure is always positive. The second important property, thermodynamic property, is what is known as the critical temperature. Critical temperature means it is the temperature at the peak of the vapor dome, where the latent heat of vaporization becomes zero. So, if the critical temperature is lower, then what would happen is the condensation would be closer to the critical temperature, and if the condensation is closer to the critical temperature, the performance would drop sharply. This you can understand by drawing the vapor compression refrigeration cycle on a pressure enthalpy diagram. And you can imagine that if you have a low critical temperature, then the spacing between the critical temperature and the and the condensation temperature would be much less. So as a rule of thumb, the critical temperature has to be greater than 1.5 times that of the condenser temperature. It means that the critical temperature has to be high so that the COP is much better. If you have a lower critical temperature, the COP would drop sharply. It means that if the condenser temperature approaches the critical temperature, then the COP would be much lower. The third important aspect is what is known as the latent heat of vaporization. So the desirable property for the refrigerant is that the latent heat of vaporization has to be high. That is because the basic refrigeration principle is that the heat is absorbed for the phase change in the evaporator. So a high latent heat would provide high refrigerating effect per unit mass per kg of the refrigerant. And if there is a high latent heat, the system would require a smaller mass flow rate. If there is a smaller mass flow rate, the compressor's size would be smaller, and if the compressor size is smaller, the system efficiency improves, the coefficient of performance improves, as well as the cost of the system would also reduce. So a higher latent heat of vaporization is desirable property for a refrigerant. The next thermodynamic property which should be considered in selection of refrigerant is the vapor density or the specific volume of the vapor. You know that specific volume of the vapor is the reciprocal of vapor density. So higher vapor density means a lower specific volume, and the lower specific volume means the smaller compressor displacement. If the vapor density is lower, it means that the specific volume is higher. If the specific volume is higher, then we will have to have a larger compressors. So generally, when we are talking about small capacity compressors or small size compressors, then and if you are aiming for small size compressors, then we need to go for refrigerants which are having a higher vapor density or a lower specific volume. For example, R290 has a higher vapor density than R134A, and hence we need to use more compact compressors with R290 as compared to R134A. If you want to use centrifugal compressors, then the vapor density has to be lower. The third important property is what is known as the compression ratio. A lower compression ratio is preferred because it would deliver multiple operational benefits that extends the equipment life and improves the efficiency. By compression ratio, we mean the delivery pressure upon the suction pressure ratio. It is also called as the pressure ratio. And if the pressure ratio or the compression ratio is lower, then the discharge temperature is lower. If the discharge temperature is lower, the compressor life is more. Similarly, if the compression ratio or pressure ratio is lower, the volumetric efficiency improves. So, a higher compression ratio is not desirable, a higher pressure ratio is not desirable. Mind well, here I am using this compression ratio terms to denote the delivery pressure upon the suction pressure, that is the evaporator pressure. Okay, so compression ratio is used as a synonym of pressure ratio. The other parameter is called as coefficient of performance, which is again the function of enthalpy difference, the pressure ratio, and the heat transfer characteristics. So, if the saturation curve, that is the pH diagram or the vapor dome, is flatter, then we would see that that refrigerant whose pH curve is flatter would give us the higher coefficient of performance, and the system would be more energy efficient. The other set of properties along with the thermodynamic properties which are equally important in the choice of refrigerants are called as physical properties. So the physical properties of the refrigerants would influence number of parameters, could be like heat transfer, the pressure drop, the leakage, as well as the manufacturability. These physical properties would determine how the refrigerant is going to behave in the real world operating condition. So the key physical properties include the thermal conductivity, the viscosity, the specific heat, and the dielectric strength. What is generally desirable is a higher thermal conductivity, because a higher thermal conductivity would ensure better heat transfer and the heat exchanger size would be reduced. For example, ammonia has an excellent thermal conductivity. Viscosity is desirable as it reduces friction. It reduces friction and hence it reduces frictional losses. If the viscosity is lower, the friction is lower, and if the friction is lower, the losses would be lower. So a low viscosity refrigerant is always desirable, and it would also improve the oil return in the system. High thermal conductivity, low viscosity are thus the key physical properties. Lower specific heat, lower liquid specific heat is desirable because it reduces the throttling losses in the expansion device. Now, how is that so? For that, you need to be clear on the representation of the cycle on the pressure enthalpy chart, because a lower liquid specific heat means the temperature required, the heat required to change the temperature is less for the condensate. Liquid means condensate, because liquid in the vapor compression system is obtained after condensation. Okay, so if you have a low liquid specific heat, then your throttling losses would be reduced in the evaporation expansion devices. Dielectric strength is another important property, especially for the hermetically sealed compressors. If there is a poor dielectric strength, that would lead to the failure of the motor insulation. Density, both the liquid as well as the vapor density, they significantly affect the vapor compression system design as well as its operation. Because you know that if the density, it is the density which determines the diameter of the refrigerant lines throughout the system. The pipes through which the refrigerant flows, its size, its internal diameter is a function of density. Similarly, the frictional losses and energy efficiency because of the pressure drop is also directly related with the density. Impacts of density could also be on the oil return, lubricating oil return, because you know that in the refrigeration system, the lubricating oil has to come back to the compressor, and this job is done by the refrigerant vapor. The third set of properties in case of selection of refrigerants are called as chemical properties. The chemical properties would influence safety, durability, and compatibility with the system components. So, chemical properties basically function are concerned about how the refrigerant is going to react with the different materials which are used in the system, the lubricants which are used in the system, and the impact of those on the performance over a long period of time. One important thing is the refrigerant whichever we use has to be chemically stable. By chemical stability, what we mean is that the refrigerant should not decompose at a higher temperature, because if it decomposes, then it would have an adverse impact on the system. It would corrode the materials which are used. For example, ammonia corrodes copper, which is the design constant, and we cannot use copper if wherever ammonia is used as a refrigerant. Second thing is the refrigerant should not corrode the other critical elements like steel structural components or the aluminum evaporators or the seals and the gaskets, because if they are damaged, that would create leakages and it would impact on the performance of the system. So both the chemical stability, that is the refrigerant should not decompose at high temperature, high pressure or presence of oil or metals, as well as the corrosion resistance are equally important in the choice of refrigerants. A third and the most important chemical property is the flammability. So if the refrigerants are flammable, then they are not recommended for your domestic applications. Uh, Generally, the categorization is in terms of A1, A2, and A3, where A1 is considered very safe, non-flammable, whereas A3 is considered not at all safe, it means highly flammable. Hydrocarbons, they are efficient thermodynamically, but they are A3 types of refrigerants, meaning that they have a tendency to, they have a high flammability, and hence we need to have a careful special handling of this refrigerants. Safety is at of concern. Toxicity could also be important in the selection of refrigerants. Industrial systems can tolerate moderate toxicity, but for comfort air conditioning, a very low toxicity is important. So, in that case, again, the ASHRAE classification is important to make sure that the less toxic refrigerant is selected for the household or comfort application, and a relatively toxic refrigerant might be selected for industrial application. As I said earlier, compatibility with the lubricant, essentially like compatibility with mineral oil or POE, all this is important because that is going to affect the life of the components in the long term. If there is an incorrect pairing, it means that if you have a refrigerant which is uh, going along with an incompatible lubricant, then that might lead to the oil logging or the compressor seizure, and that would result in the catastrophic systemic failure. So, in order to ensure that there remains a proper lubrication in the long run, the refrigerant has to be compatible with the uh, lubricant. There has to be a critical pairing. Environmental properties have now come to dictate the choice of lubricant because of what are known as the Montreal Protocol and the Kigali Agreement, which put a regulatory constraints on the choice of refrigerants by these two parameters, namely the ozone depletion potential, and second one is the global warming potential. Or there is also one more parameter which is called as total equivalent warming impact, or TEV. So ozone depletion potential would basically measure the refrigerant's potential to damage the stratospheric ozone layer. And that was the reason why CFCs, chlorofluorocarbons, and now SCFCs have been phased out globally because they have high ODP values. And the second important parameter, as I said, is GWP, which is the global warming potential. And now the low global warming potential is mandatory in the new system design. For example, R134A has a GWP of approximately 1430, while that of 12234YF has a global warming potential which is less than 1. So from a global warming potential then, instead of R134A, R1234YF is desirable refrigerant. Which I mentioned earlier about the safety classification, that toxicity is low and flammability is none. That comes safest refrigerant category E1. And if the toxicity is high and the flammability is medium, that comes under a category group B2. Similarly, E3, E2L categorization is provided here on this slide, and this classification is based on ash rating. Refrigerant selection must align with the specific application requirements, because as I said, the evaporation temperature has to be above the temperature at which the has to be mapped with the temperature at which the system has to be maintained. For example, household refrigerators we need to maintain at lower temperature, negative temperatures. Ultra low temperatures are in ULT systems. In air conditioning systems, relatively higher temperatures are required. These are some typical refrigerants which are used widely. Domestic refrigerators R134A or R600A. Commercial HVAC systems R134A or R1234YF. Industrial and specialized systems, ammonia is much more common. It remains the preferred choice for large industrial systems due to its excellent thermodynamic properties, as well as zero ozone depletion potential and global warming potential, and a much better coefficient of performance. However, ammonia remains toxic. In a very specialized application like ultra low temperature cascade system, there are two refrigerants which are used, one refrigerant in the high stage and the other refrigerant in the low stage. Low stage is low boiling, high stage is high boiling. So that is typically for your medical and research applications. So key important parameters, key important things we need to keep in mind when selecting the refrigerant is it is a multi-parameter decision, meaning that refrigerant selection requires balancing thermodynamic performance, safety, environmental impact, and the cost considerations. It is not that simply one set of properties would do. Second thing is property matching. We need to match the refrigerant properties to specific applications for the optimal performance. Third is, and it is critical now, that these refrigerants have a lower ozone depletion potential and lower global warming potential, which is now mandatory. And finally, those refrigerants which are being chosen, they have to be very safe. Considering the ASHRAE safety classifications, refrigerants are to be selected, and the compatibility with the lubricants and system materials is equally important considering the life of these equipments. I hope that this clarifies much of the aspects of how the refrigerants are selected, which properties matter a lot, and it would help us understand in real world how a choice of refrigerants is made by a multi-parameter decision making matrix.